Hello, hello. So welcome to part 2 of my talk on infrared absorption spectroscopy fundamentals. In part 1, we talked about the fundamental physical basis of infrared absorption spectroscopy, how it probes chemical groups, and a little bit about spectral interpretation. So in part 2, what we're going to go over are more practical aspects of actually doing a measurement, some aspects about instrumentation, and in particular what sort of artifacts that you need to be aware of when you actually do an FTIR measurement. So before we begin, there's some information I just want to quickly touch on. So to start with, FTIR is not the only infrared vibrational spectroscopy technique out there. There's also Raman scattering. Raman scattering is based off of a different physical mechanism, and it has also different mechanics and different instrumentation. I'm not going to go over all of this slide. If you want, you can pause the video and read through it. But the short version is that FTIR and Raman spectroscopy are sister techniques. They are very, very complementary. They both probe the same vibrational frequencies, but peaks that show up very strongly in FTIR don't show up very strongly in Raman, and vice versa. So, for example, we talk sometimes about the disulfide bond or disulfide group. The disulfide bond does not absorb very strongly in FTIR at all, but they will show up in Raman very, very strongly. If you're more interested in Raman, there are a few nice videos by this guy named David Tuchel on YouTube. I believe David is a Horiba application scientist. I highly recommend those videos if you're interested in learning more. The other thing to note that I'm not going to necessarily cover over fully is that there are a lot of factors that affect the group frequencies, the vibrational frequencies. And this might be a little daunting at first because it can really kind of complicate spectral interpretation. But on the other hand, sometimes you can use these factors to your advantage. For instance, if you know that crystallization of your sample will change the peaks in a specific way, then you can use FTIR to probe the crystallinity of your sample. So we're going to be talking specifically about FTIR measurement modes, and there are a handful of different modes depending on what your sample is and what you're interested in looking at. So the main modes are transmission mode, attenuated total reflectance or ATR mode, diffuse reflectance, and specular reflectance. By far, the two most popular modes are transmission and ATR modes. And these days, I believe ATR is probably the most popular FTIR mode out there, for the main reason that you need almost no sample preparation to take a measurement. However, it is still important to understand transmission mode for a couple key reasons. So we're going to start off with talking about transmission mode FTIR. So this is a photograph of the machine, and this right here is the transmission mode module. I actually just took it out and put it on the machine just to take a picture of it. Right now, the ATR module is the one that's actually installed, but it's really easy to swap these modules in and out. It's fairly trivial. Transmission mode FTIR is probably the easiest mode to understand. All you have to do is take your sample, slot it into this vertical holder right here, fire an infrared beam through it, and detect what gets absorbed. That's pretty much it. So the key difficulty here is sample preparation. You're not always going to have a sample that can be made into a self-supporting thin film. So for instance, if you have a liquid or a powder, what do? There are a couple options. You can cast your sample onto an infrared transparent substrate, or if you have a powder, like I had to do in graduate school, you grind that powder up in a mortar and pestle with some potassium bromide salt, and then you take that mixed powder and you put it into an anvil and press that powder into a solid pellet that you can then put into the machine. Now, all of the artifacts, or most of the artifacts related to transmission mode FTIR are going to be related to sample preparation. So for instance, if you're dealing with a thin film, then you can get film thickness interference fringes. If you're dealing with solvent, then you can have residual solvent, or if you have a substrate, then you have to deal with residual absorption of the infrared beam by that substrate, so on and so forth. However, it's important to understand the differences between transmission FTIR and ATR FTIR. On the software of some instruments, you can have library of spectra available to you that you can compare your data to. And that can be useful if you have an unknown sample and then you're trying to find out what's in your sample by comparing it to this historical data. The problem is that most of that historical data is taken in transmission mode. And there are a couple of very key differences between transmission mode spectra and ATR spectra. If you don't account for those differences, then your comparison is going to be wrong. So you have to understand those differences. So let's talk about attenuated total reflectance, FTIR. So this is a close-up photograph of the ATR module, and right here in the center, this little itty-bitty bit there, that is the diamond crystal. All you have to do is put your sample right on top of that diamond and take a measurement. That's it. So what happens is that the infrared beam gets fired into the diamond crystal from below, and it gets reflected off of the diamond sample interface. So then it gets bounced back down and gets fed into the detector. So the condition for this measurement to work is total reflection. If you go to, say, classical optics and Snell's law, then that means that you have to satisfy this critical angle of reflection. The critical angle has to be greater than this ratio between the sample refractive index and the crystal refractive index. If you do not satisfy this condition, you're going to get a lot of spectral anomalies. Now, what you might say is, well, if it reflects off of this interface, it doesn't actually enter the sample, does it? Then how does it actually measure the sample? Well, when it reflects off of this interface, what is created is an evanescent wave. This is a non-propagating electromagnetic field. It's basically a very concentrated electromagnetic field right at the interface. The amplitude of this wave decays exponentially with distance from the interface. So going back to this total reflection condition, most of the time you actually don't have a lot of say in your setup. Usually you have a diamond crystal, you have a single reflection, and a fixed reflection angle of 45 degrees. Diamond has a refractive index of 2.4. If you want, you can get a germanium crystal that is a higher refractive index, but it tends to be more expensive and tends to be less durable, so you have to be very, very careful with it. Because you have this fixed setup, what you really have is not necessarily a critical angle, but a critical sample refractive index. Your sample refractive index has to be less than 1.7. If it is higher than that, then you are going to get some severe spectral anomalies. So ATR requires almost no sample preparation, but that does not mean that it is an artifact-free measurement technique. And there are a handful of artifacts that are endemic to the measurement, and most of which we're going to cover. So the first thing to consider is the transparency of the diamond. The diamond is not perfectly infrared transparent. This is a plot of the transmittance of the diamond in the infrared range. Typically, we take a measurement somewhere around the 4,000 to 400 wave number range. And you'll notice a couple key spots where the transparency dips. These are spots where you are likely to get increased noise or spurious peaks. So the first spot is in the center location around 2,000 wave number. That's usually not as much of a problem because that's out in no man's land. What gets a little bit more troublesome is right at the edge of your spectral range, right around 500, where the transmittance of the diamond drops off precipitously. So trying to analyze peaks out in this range becomes a little difficult. You can very easily get very high noise and spurious peaks occurring there, so you have to be careful. The second thing to note is I mentioned that the evanescent wave decays exponentially with distance into the sample, and that decay length is also called the penetration depth, dp. The equation for dp is given right here. So NC is the crystal refractive index, and S is the sample refractive index, and very importantly, it depends on the infrared wavelength. So actually, the penetration depth at low wave number is going to be higher than it is at high wave number. If you estimate, say, a sample refractive index of 1.5 and plug those values into the equation, what you see is that at around 3,000 wave number, the penetration depth is less than a micron out in the hydrogen stretching region. But once you go to the opposite end of the spectrum at around 600, the penetration depth is now more than 3 microns. And with a deeper penetration depth, you have more chances to absorb the infrared energy. So the absorption peaks at low wave number in ATR tend to be higher than at high wave number compared to transmission mode spectra. This is a very, very key difference. So the high wave number peaks appear smaller in ATR than they do in transmission. Now, some software have a function that can correct for this to some degree. So what I have plotted here in the red is an actual ATR spectrum of bitumen. And plotted in the green is a computer correction estimating a sample refractive index of 1.5 that sort of models what it might look like as a transmission mode spectrum. And as you can see, what you notice is that the high wave number peaks in transmission will appear much larger, and low wave number peaks are severely depressed. This is the main correction that you have to engage in when you compare your ATR spectra to the library spectra. So the last artifact that I'm going to go over is the ATR dispersion artifact, and this is a doozy of an artifact. Fundamentally, this artifact occurs when the total reflection condition is violated due to high sample refractive index. But for years and years and years of doing FTIR, I never got a satisfactory description in my mind of what this artifact does. Most of the time when I looked it up, it would show a diagram that looks sort of like this. And the explanation was because the total reflection condition was violated, the beam penetrates deeper into the sample, and then you get a different beam path, and then you get artifacts related to that. But it still showed a beam that fully reflected back into the diamond and reflected off of something in the sample. It wasn't very clear, and it was kind of poorly described. So it wasn't until I found this paper right here that I started to more fully understand what was going on. So I'm going to describe this artifact in the way that I understand it. It may be slightly inaccurate, but this is how I understand this artifact, and I think it's a little bit of a better explanation. And there are three key effects that happen when you violate the total reflection condition. So first off, the beam does not reflect off of some magical interface within the sample. The beam still reflects off of the diamond sample interface. But because the total reflection condition is violated, what that means is that you get a portion of the beam that is transmitted. It propagates into the sample. That portion of the beam, most of it does not come back. And because it doesn't come back to the detector, it's registered as a quote-unquote absorption by the machine. So partial transmission leads to an elevated baseline absorption. Across all wavelengths, you're going to get an elevated quote-unquote absorption registered by the instrument because part of the beam is just simply going into the sample. So this particular effect, usually we don't notice it because when we work up the spectrum, a lot of the time we just subtract out the baseline. And so we don't notice this happening most of the time, which actually makes the next effect appear much more confusing if we don't understand what's going on. So the second thing that happens is that you can start to get anomalous peak shape due to change in refractive index as a function of wavelength. So the key point here is that the refractive index is not a constant. Around an absorption peak, the refractive index function will take on a very severely nonlinear shape. There is a lot more to optical physics, and I'm not an expert on it. Refractive index and absorption index are related by Kramers-Kronig relationships, etc. But the refractive index does not stay constant. And even if you start off with a sample refractive index that is below 1.7, that satisfies total reflection, what can happen is that at the low wave number side of an absorption peak, the refractive index, as you can see in this diagram, can jump upwards above 1.7. And when that happens, then you violate total reflection and you get a bit of anomalous absorbance. In the most extreme case, you'll actually sort of tack on this function to the peak shape. So instead of a nice sharp peak like you see plotted out in blue, what you will see is something like this. At the high wave number end, the refractive index dips down, so it actually satisfies the total reflection condition better and you get good reflection. But at the high wave number end, you get higher anomalous absorption. And you start off with a higher baseline as well, so that's where the higher baseline comes in. The other thing to note, as I've plotted here, is that because of this absorption at this tailing end of the peak, the peak value is going to be shifted a few wave numbers lower in ATR than it is in transmission. And this will happen even if you don't have this severe distortion in the peak shape. Even if you are dealing with a sample that is normally satisfies the total reflection condition, because of this anomalous absorption, you can get this slight shift in the peak wave number, and also you can get longer tails on the low wave number side of the absorption peak. So this is a key thing. The absorption peaks in ATR will appear slightly lower in wave number than they might normally in transmission. The last thing that happens is that even though this wave propagates through the sample, sometimes you can get scattering of some of the infrared intensity back into the diamond. But the thing is that this scattered light is now following a different beam path. And if it's following a different beam path, then it's going through a different amount of diamond. And if it's going through a different amount of diamond, then it's going to be absorbed to a different degree by that diamond. And your background that you took no longer applies to the scattered radiation. So you will start to see anomalous diamond absorption peaks in your spectrum, among other things. So those are the three main effects of this dispersion artifact. These come up a lot when you're measuring materials like carbon black or graphite or char that have high refractive index. So that is pretty much it. If you have any questions, you can contact me. Thank you for listening.